As we have seen so far, 5G network supports a range of services, and different kinds of services place different requirements on the network. For example, AR and VR services need a lot of bandwidth. Self-driving vehicles need the latency to be extremely low, and Internet of Things will need an enormous number of connections. So 5G networks must be able to meet different requirements for different service scenarios. They have to be like a giant buffet. Some people go for the seafood, some people go for the roast beef, some people are only interested in the desserts, and some people spend most of their time at the salad bar. You can pick and choose the parts you like based on your own tastes. Looking ahead, how do we think 5G will be able to adapt all these different requirements? The answer is network slicing. What is network slicing? Network slicing is a process where a physical 5G network is divided into discrete end-to-end logical networks. Different logical networks, or slices, carry different services. It's like how a big road can be divided into different lanes. There are lanes for cars and lanes for public transportation only, and shared bicycle pickup points where you can grab a bike after you get off the bus. The car lanes might have convenient off-ramps that take you directly into a gas station, and the bus lanes will have bus stops at regular intervals. What is the value of network slicing? Network slicing provides two main sources of value: high-quality services and lower CapEx. Network slicing allows for more efficient, more nimble service differentiation, and by keeping these slices isolated from each other, quality can be more easily guaranteed. Network slicing also gives telecom operators a chance to enter vertical industries and expand the range of services offered. Network slicing can provide differentiated services less expensively, which makes network construction less expensive. Since if network slicing is so good, how do we make it a reality? Well, let's start with a look at how a wireless network is sliced. The most precious resources on a wireless network are time-frequency resources. The signals transmitted by your mobile phone go through the base stations in the form of electromagnetic waves. The electromagnetic waves are comprised of different frequencies at different time slots. So, how do we divide up time-frequency resources? Currently, there are two methods: hard slicing and soft slicing. With hard slicing, frequency resources are allocated to three main 5G scenarios: eMBB, MMTC, and URLLC. Each category of service only has access to the specific spectrum that have been assigned to that type of service. It's like a giant conference center, with all sorts of rooms, large and small, filling up 3 floors of the building. Company A can use any of the rooms on the first floor, but only those on the first floor. Company B gets full access to the second floor, and Company C gets the third floor. But what if Company A has a large number of people, but Companies B and C only a few? The conference rooms on the first floor would end up really crowded, while there are plenty of rooms to spare on the other 2 floors. This is the problem with hard slicing. A lot of resources can end up being wasted. If soft slicing is used, time-frequency resources do not need to be sliced in such a one-size-fits-all kind of way. Some resources can be reserved for emergency services, while others are allocated dynamically on a scenario-by-scenario basis. Going back to our example with the rooms in the conference center, some number of the rooms can be reserved for upper-level management, but then the rest of the rooms can still be scheduled in a more flexible manner. Each time a group of people show up for a meeting, an appropriate room can be assigned based on how many people will be in attendance. In this way, the conference room's resources can be allocated more appropriately, and you won't have some rooms being so crowded while other rooms are left empty. This is the advantage of soft slicing, and it's also a common way to allocate resources in today's telecommunications systems. Now that we've reviewed how radio network resources are allocated, let's move on to the transmission network. The most valuable resources on the transport network is bandwidth. You might have 100 megabit per second available, 1 gigabit per second, or 10 gigabit per second bandwidth. On the core network, there could even be 100 gigabit per second of available bandwidth. So, how do we break it up? The transmission network uses technologies such as FlexETH to divide link bandwidth resources. On a big road, the police can divide the lanes using a physical barrier. On this road, the small lane on the left has been set off for automobile traffic only. The lane on the right is for bicycles, and the one in the middle is reserved for buses only. Because there is a physical barrier, there is no way for vehicles to cross over into another lane. The lanes cannot be shared, just like bandwidth resources cannot be shared between different slices on transmission network. This resource isolation ensures that services are isolated and secure. But within any given lane, the manufacturer of the vehicles doesn't matter. All that matters is that they are in the right category of vehicle. And in any given slice of a transmission network, the services on that slice share all of the bandwidth within that slice. This ensures that the resources of each slice can be used more effectively. That leaves just the core network. Let's see how network slicing works on the core network. We already learned that core network devices are based on an NFV architecture. All NE functions are stored in the server as software. But there's another feature we need to discuss: functional modularization. Every NE only does one thing. Like as a 5-star restaurant, there are chefs, waiters, dishwashers, hosts, and usually a sommelier. It's not like a small family restaurant where the boss has probably done every job there at one point and frequently still does them from time to time. Actually, the biggest advantage of functional modularization is the convenience being able to create customized functions. For example, when designing an Internet of Things (IoT) slice, most M2M terminals are not mobile, so there's no need to provide functions related to mobility. Those details can be omitted from the design. Functions can be tailor-made to fit specific service requirements, which allows them to be deployed more quickly. So, we have core network functions that can be tailored. Is that all we need? Obviously, that's not enough. When designing different slices, we need to consider how the services provided using different slices call for core network NEs to be deployed in different physical locations. For example, voice services are sensitive to delay. So, when designing this slice, we need to deploy the user plane functions of the core network closer to the user. That's why there is less distance between the mobile phone and the egress gateway, and voice call delay is reduced, which means the end user's experience is improved. 5G networks must be sliced to meet the diverse service requirements of future 5G networks. Network slicing improves service quality of service awareness. Network slicing also enables carriers to provide a range of new services as inexpensively as possible, and to expand the existing range of service scenarios. When network slicing is used, wireless networks mainly divide up time and frequency resources. Transmission networks mainly divide up bandwidth. The core network mainly divide up NE functions, and allows these functions to be flexibly deployed in different physical locations based on specific service requirements. In this lesson, we learned about 5G network slicing and how it's implemented wireless, transmission, and core networks. That wraps up this lesson. In the next lesson, we will discuss the 5G network structure.